to start with 5.1 today. This will probably be like the rockiest part of chapter 5 just because it takes a little bit to get rolling. Okay? But what we're going to do is introduce fundamental trig identities, and then we're also going to work on some practice problems where we simplify expressions. So we're going to start with the basic reciprocal identities, and we have 6 reciprocal identities. Now you are probably, or should be, very familiar with the reciprocal identities for cosecant, secant, and cotangent. In order to do your chapter 4 test, calculator portion, you were basically using reciprocal identity because your calculator doesn't have a cosecant, secant, or cotangent button. So what do you know about cosecant x? It's equal to what? 1 over sine x. That's the reciprocal identity. So cosecant x is equal to 1 over sine x, secant x is equal to 1 over cosine, and cotangent is equal to 1 over tangent. Now, those 3 had a lot of meaning to us in chapter 4. We needed them in order to be able to do those calculations in our calculator. The other 3 reciprocal identities, they're true, and we're going to use them in this chapter 5, but we didn't really make use of them in chapter 4. And it's less common for us to use these reciprocal identities to do the math work. You can sit wherever you want. Less likely to use this to do actual math because we feel more comfortable with sine, cosine, and tangent. So for sine, we're just going to say that it's 1 over cosecant. Cosine is 1 over secant, and of course tangent is 1 over cotangent. And so we're less likely in chapter 4 or other chapters to use that because we're more comfortable with sine, cosine, and tangent. But we will be using these trig identities in chapter 5 because we're going to be rewriting things. So if you ever notice that you have a secant x in a denominator, you can really write that as cosine x in the numerator. So we're going to be able to move things like in a fraction from top to bottom, okay, using the reciprocal identities. All right. Next up are quotient identities. And there's only 2 quotient identities. There's one for tangent and one for cotangent. I saw some people on the chapter 4 no calculator part of their test using the quotient identities. That may be because they looked in the book or looked online for some extra help when they were working on tangents. And I'm going to give us a visual here that I'll use again for my Pythagorean identities. Suppose this is my unit circle. Remember that the unit circle had a radius of 1. And we had talked about that day we had the pink and blue triangles and we did the bow ties or butterflies all the way around. We had talked about those XY coordinates, and they represented the side lengths of the right triangle, right? X and Y. And then we decided by definition of trig ratios, like opposite over hypotenuse, adjacent over hypotenuse, etc., that when we did this on the trig, on the unit circle, the cosine was always x over 1, which was just x. So we could also say that this side that we have labeled as x, that's also just cosine theta. And this side that we have labeled as y is sine theta. So now, think about the trig definition for tangent. You probably remember tangent is y over x. We could also write that as sine over cosine. Okay, so our quotient identity is sine x over cosine x. Now, notice I'm using x's right there. You're going to see when you do your homework assignment in the book, they're going to use thetas, betas, all sorts of letters, y's. It doesn't matter what we put, but something has to always be behind a trig function. You can't just have tan. That doesn't mean anything. And then, of course, what would cotangent be? Cosine over sine. Okay, now, those quotient identities are going to be super helpful because one of my tips later on is, if possible, get everything in terms of sines and cosines. And so this is a great way to turn tangents and cotangents into sines and cosines. All right, next up we want to talk about Pythagorean identities, and I'm going to use my same picture that I have up here. Pythagorean makes me think about Pythagorean theorem, a squared plus b squared equals c squared. In that triangle that I have drawn on the board, I could say x squared plus y squared equals 1 squared or 1. But if I'm thinking about trig ratios, I could also say cosine squared plus sine squared equals 1 squared or 1. And so that's our first Pythagorean identity. Now, it doesn't matter which way you write it, sine squared plus cosine squared or vice versa. They're going to be the same thing because addition is commutative. Okay, so don't worry too much about that. Now, a couple of quick things about Pythagorean identities. Notice the way that we write sine squared or any trig ratio squared. The square comes after the trig ratio sine, cosine, tangent. And that means you're taking a sine x times a sine x. So you're multiplying the sine by itself. Okay. We don't want to write it like this because we could read that as sine of x times x. And that's not what we want. We want a sine times a sine. That's what we want. So that's how we write our sine squareds, cosine squareds, etc. And the other thing to note about Pythagorean identities is this is not the only way this can be written. So like we can change this. Let's say somewhere in my work I had a sine squared. Well, I could solve this to get sine squared all by itself. Just subtract cosine squared x from both sides. So another version of that same Pythagorean theorem is that the sine squared x is equal to 1 minus cosine squared x. And you could write a second one that says cosine squared is equal to 1 minus sine squared. So you're allowed to like algebraically manipulate those equations by adding and subtracting from both sides to make it look like what you need. Now there are two other Pythagorean identities. I'll have you write these down, and you might use them. Just in the interest of time today, I'm not going to go through like how we get them, but we can look at that later this week on a day we have more time. Like why does 1 plus tangent squared equal secant squared? Why do those two go together? And again, you can rearrange all of the Pythagorean identities. Okay, so if we wanted to solve for tangent squared x is equal to secant squared x minus 1. Okay, so you might see it look different. I just always know to be on the lookout for Pythagorean identities. Really, anytime I see a trig function that's squared, I think about it. And if I see a trig function squared with a 1 or a negative 1, then I'm really thinking about Pythagorean identities. Okay, so it's just kind of like a callback to that. Okay, now we're also going to jot down the even odd identities, but if you want to make a note in your notebook, the three that I just went through, reciprocal, quotient, Pythagorean, you have to know. Quiz on Friday, you should be able to write those down. Reciprocal, quotient, Pythagorean. Even odd identities, I'm not really going to ask on quizzes and tests, but it's at least worth a mention for us. It actually goes back to something we covered in first semester, which are even and odd functions. And that's why the identities work out the way they do. So notice currently on the screen, I only have tangent and sine families, like cosecant and cotangent are up there, but nothing about cosine or secant is here. Okay. And the reason why I only have these grouped is these are odd functions. And this is going to be like a real long trip back to first semester chapter 1. Do you remember when we were checking if a function was odd or even? And we would do something like, is f of negative x equal to negative f of x? And we would like have to substitute it in and see what happens. We're not doing that algebraic test anymore. But this is always true of odd functions. When you put in a negative x, the output is negative. So that's what you're seeing in these identities. When you put in a negative angle, you just get the negative sine function out. Okay? And same thing for tangents. If you put in a negative angle, then the tangent turns negative. And that goes back to the idea that they're odd functions. So here's a tangent function. A tangent function has asymptotes at negative pi halves and positive pi halves. And it passes through the origin right there like that. And if you'll remember, odd functions are symmetric to the origin. They have like a rotational symmetry. Okay? And so you can see that. And also, if you think about it like this, like here's an x, and then here's like your tangent x. If I were to, instead of going right x, if I were to go left x, then I'm getting out a negative tangent x, like it turned negative because I went down. So that's why those identities are what they are. Cosine is not odd, it's even. Does anybody remember what even functions are symmetric to? Odd functions are symmetric to the origin. Even functions are symmetric to
Y-axis.
the y-axis. Yep. Good. Thanks, Liam.
You're welcome.
So this is an even function. In an even function, when we would do f of negative x back in chapter 1, it would just equal the original f of x. Thanks. And like Liam said, it's symmetric to the y-axis, so we know that cosine looks like this. If we, like continue that on the other side, you can see how it's symmetric to itself. So when I just change the value of the x, it's at the same y value on the other side. So if you ever notice anything like that, and like in your homework, that there's like a negative inside of a trig function, remember, you can either bring it out front of the trig if it's sine or tangent or they're reciprocals, or it just turns back into a positive if it's cosine or secant. You can ignore it. Okay. So before we get into the actual simplifying of trig expressions, I also need to have a quick chat about factoring trig expressions. And this sometimes can, give people some trouble, but what I like to say is it's just factoring polynomials. So if you could factor polynomials from Algebra 1, then you can factor trig expressions. What's different is instead of having things like x squared and x, you're going to see that you might have a sine squared x and a regular sine x. So then you're like, oh, maybe I could factor out a sine. Or maybe it's a trinomial, so I could factor that. So we're going to do a couple of examples. I'm going to start with all the colors. I'm going to start with the one on the left. 2 cosecant theta minus 7 cosecant theta plus 6. So remember, it doesn't matter if I have x's or thetas or betas or whatever behind the trig functions. Note that you should always have something behind them. You should never just have CSC out there all by itself. What I like to do for people who struggle with this is like see how like there's 3 separate terms that are being added or subtracted. If cosecant squared and cosecant really cause you a lot of trouble, just think about them like variables. Like you'll know what they are, so you don't have to worry about them so much. It's almost like I'm asking you to factor 2x squared minus 7x plus 6. Right, where x is just cosecant theta. And so if you're factoring a trinomial, those are the problems where you have 2 groups of parentheses. And if it's a polynomial, I would like stop at my first term. Like what would multiply to make 2x squared? 2x and x. So what multiplies to make 2 cosecant squared? A 2 cosecant theta and a cosecant theta. So 2 cosecant theta and a cosecant theta. Okay, that gets me my first term. Now, I usually jump to the back of the trinomial and I say like, what will multiply to give me positive 6? 1 and 6, 2 and 3. It needs to multiply to be positive, so they have to be the same sign, but I can see in my middle term it's negative, so they must both be negatives. Okay, so I'm going to go ahead and put in my signs, minus. If it's a negative 6, then I know one's positive and one's negative, and I don't know which one. Okay. And then this is where I just use like a little bit of guess and check. You know, like, is it 6 and 1 or is it 2 and 3? It depends, because something's going to get multiplied by 2. Can anybody see which one is the factors I should use, Dylan?
I should use
2 and 3. If I put a 2 in this last piece here, when I FOIL it out, 2 cosecant theta times 2 will be 4 cosecant theta. And then I'll have, on the inside, I'll have a 3 cosecant theta, which will get me to that negative 7 cosecant theta. And then, of course, negative 3 times negative 2 is still positive 6, so factors. If you're not sure, FOIL this back out. And if you're really having trouble, try factoring without all the trig. Right? So like some people might be able to see this better if they're just looking at the x's and not the cosecant thetas. Oh, it's got to be 2 and 3 and a minus, and they can easily see their negative 7. Okay, but where your x's are, those are cosecants. The second one that I have up there, this one's a little bit tricky. Often it gets overlooked when you're simplifying because they're not the same trig function. You know, like I kind of knew I might factor here because I had 2 cosecants. But there I have a sine squared and a cosine squared. You might first think about Pythagorean identity, but it doesn't match the Pythagorean identity because they're supposed to be added. So there's no way for me to rearrange it and get one positive and one negative. What I have right there is a difference of perfect squares. So in a difference of perfect squares, like a squared minus b squared, that factors to be a plus b, a minus b. You know, like think about how do you factor x squared minus 25? X plus 5, x minus 5. So when we factor this, we'll have sine theta plus cosine theta times sine theta minus cosine theta. So that would give me my sine squareds in the front, it would give me my negative cosine squareds in the back, and my outsides and insides are going to be opposite signs, so sine theta, cosine theta, and then negative sine theta. Okay. So there's going to be a little portion of the homework where you're trying the factoring, and it's some of us will catch on real quick, and some of us will really struggle. If you're really struggling, then my recommendation to you is try to write it without the trig there. Just use variables instead, like square what's squared and whatnot. In this one, you have to write it as two separate variables, like I used a squared and b squared. But try writing it like that and try factoring like you would from Algebra 1. Okay, we're almost to the good parts of this. I just have a few tips. Okay. The textbook is going to say, using your fundamental trig identities, simplify these trig expressions. And these are my tips to you. Try getting them in one type of function. Like, think about this. If you could rewrite everything so it was all cosines, that might be really helpful because then maybe cosines add together or cancel out. Something good might come of that. So try getting it all in one trig function. If you can't get it in one trig function, try getting it in all sines and cosines. That's why those quotient identities are so awesome for tangent and cotangent, because if you have tangents and cotangents mixed in, you might be able to get all cosines and sines. You can always look to see if something factors. Sometimes when you factor, then maybe you'll be able to cancel something. Or factoring might reveal like a Pythagorean identity or something like that, since the Pythagorean identities have plus and minus in them. And then the last one tip that I have is combining fractions. So for combining fractions, I'm just going to add two little statements here. I mean by combining fractions, like maybe multiplying your fractions or adding or subtracting your fractions. And just remember, you need common denominators to add and subtract fractions. Because you're not really doing math with numbers in this section, a lot of people like do more work for multiplication than necessary. They get common denominators to multiply, and you don't need common denominators to multiply. Just multiply across on top, multiply across on bottom, maybe see if something cancels when you're multiplying. If you try to get common denominators to multiply, you make it look a lot worse than it really is. Okay, so you only need to do that with adding and subtracting. Okay, let's get down to the good parts. Here's an example. Cosecant x times secant x minus cotangent x. And like I said, the directions in the book are just going to say, using your fundamental trig identities, simplify this expression. It means turn it into something else. It probably turns into something much simpler than three trig functions. Okay. And so this is where like that doublets activity, the word activity comes into play. Only work on changing, like one thing at a time. Okay. All right, what are some ideas that you have when you see all these trig functions, cosecant, secant, and cotangent? What might you like to do? Liam?
I think we can get them all into sine and cosine.
Yeah, one of my tips is try to get it all in sines and cosines. So, like we're less familiar with cosecant and secant. We could change those into their reciprocals. So we'll do 1 over sine x times 1 over cosine x. And I'm going to write out my reason for that, reciprocal identity. I encourage you on your homework and on your quiz, I'm going to ask you to write out your reasons. And what can we do for cotangent x? Cosine over sine. So cosine x over sine x. So with reciprocal identity, I'm also going to write quotient identity. So you might do a couple of things at once if they're not too terribly confusing. So we're really just making substitutions at that point. Now, if you're okay with this 1 over sine x times 1 over cosine x, I'm just kind of going to simplify that real fast. That's just really 1 over sine x cosine x, right? So now, what might you try? Yes, sir.
Multiply cosine of x on the cotangent on the numerator to have like denominators.
Okay, so what you're seeing now is subtraction, right? And in order to combine those as one, in order to subtract, you need to have common denominators. So I'm going to put that down as my reason. I'm going to get common denominators. This has a denominator of sine times cosine, and this one has only sine. So it needs cosine. So I'm going to multiply it by cosine over cosine. So this is 1 over sine x cosine x minus, in the top, cosine times cosine is cosine squared, and in the denominator now we'll have sine x cosine x. Now that we have common denominators, we can actually subtract. So remember, when you're subtracting fractions, because these aren't number fractions, they have trig in them, you subtract in the numerator and you keep your denominator, right? So this is going to be 1 minus cosine squared x over sine x cosine x. Through subtraction. Now you have to be careful. Don't get cancel happy. Can't cancel out your cosines because this one has a subtraction in front of it. Is anybody seeing anything that might work out nicely for simplifying? Anytime I see cosine squared, I think about Pythagorean identities. And there's a 1. In your Pythagorean identity, 1 minus cosine squared is equal to sine squared. So we can replace that sine squared x over sine x cosine x. I'm going to say Pythagorean identity. And I'm going to write that down. Sine squared x equals 1 minus cosine squared x. So you know where I got that. I subtracted the cosine squared from both sides. Okay, now what will work out really nicely? What's the same in the top and the bottom? Sine. This top, remember, sine squared x is just saying sine x times sine x. And since everything's being multiplied, you're allowed to cancel. So the sign in the denominator is going to cancel with one of the signs in the numerator. So this is going to be sine x over cosine x. So I'm just going to say, like, cancel. It's division, I suppose. And then what do you get? Tangent, Jayla says. By quotient identity. Okay. So all that stuff up at the top, cosecant x times secant x minus cotangent x, that's really just tangent x. Okay. Now the hard part for you tonight, because this is your first go-round, right? And I said it's going to be a little rocky in the beginning, is like, how do you know when to stop? Some of you might have thought, like, we were good right here, or we were good right there. So it's like, just keep looking. Is there anything else you can substitute that might make it simpler? If you keep substituting and you're making it worse and worse, stop, right? Like, if it's getting worse and worse, it's not better. Don't do it. Okay. Let's see. I want to show you real quick this example. Cosine squared x times cosecant x minus cosecant x. This is a really good example of a common mistake a lot of people make. A lot of people might look at this right away and just cancel out their cosecants because it looks like you're subtracting them, right? But you can only add and subtract like terms in math. So these things aren't like terms because this one has a cosine squared where this one doesn't. So anytime you see that where you're like adding or subtracting something and they share something in common, your first step should be a factor. Like I factored out cosecant x. They both had it, so I took it out of both terms. Okay. Then I can continue. This one is another Pythagorean identity. That's actually equal to negative sine squared. So that's times, not subtract. And then I can rewrite it all in terms of sine. 1 over sine x times negative sine squared x. So then a sine will cancel and I just get negative sine. But the purpose of that one that I really wanted to show you was that thing where, like, if they have the same thing in common, factor it out. And I have one more thing I want to show you real fast. Another thing to note is, like, I can do it in a different way that Hannah can, and we can get to the same answer. So there's not always, like, one thing you have to do first. Some of you might have used a reciprocal identity or something like that, and that would have been fine. Okay, the last example that you're going to see is something that looks like this with trig substitution. And so it does what it says it should, right? You're doing a substitution. So like it's going to give you something like this, the square root of 25 minus x squared. And then it's going to tell you what trig to substitute in for x, 5 sine theta. So I'm going to do 25 minus 5 sine theta squared. Because it's just x squared, right? And x is 5 sine theta. Well, when I square that, I have to square the 5 and the sine. So that's going to be 25 minus 25 sine squared theta. 5 sine theta times 5 sine theta is 25 sine squared. And most common mistake would be for people to square root right now. Not allowed, okay, because of the plus or minus. But they both have 25. So if I factor out a 25, then I'm left with 1 minus sine squared theta, which is Pythagorean identity. So this is 25 cosine squared theta. And now that it's just being multiplied, I can square root. So it's 5 cosine. Most common wrong answer is going to be 5 minus 5 sine theta. Please don't write that down. You cannot square root right here because of addition and subtraction. Okay, it has to be multiplication. Give those problems a go on the homework on the gold sheet. It'll be a little bit rocky, but see how far you can get. We'll talk more tomorrow.